Hello students, I am Dr. Rameshkumar, working as an Assistant Professor of Chemistry in PSN College of Engineering and Technology, Tirunelveli. Today I will be discussing on nanomaterial characterization, particularly scanning electron microscopy. So scanning electron microscopy is one of the electron probe method. So some other methods also used for the characterization of nanomaterials, but in this lecture I want to discuss only the scanning electron microscopy, which is the electron probe method. Electron probe method means the primary probe will be electron. Electron will be used for the characterization of analyzing the material properties. So electron probe characterization methods in particular are important to nanoscience because they are capable of analyzing the structure of the extremely small particles. As we know that the nanomaterials having the size range of 1 to 100 nanometer. So these methods are extremely useful for the characterizing small particles or the materials in nano dimensions. So this electron probe method use high energy electron beams. These beams are used for the imaging, chemical analysis and the determination of material structure. So most of the familiar electron probe methods are scanning electron microscopy and transmission electron microscopy. So based on the nature of the samples, we can go for SEM or TEM for the structural structural and morphological characterization. So in the SEM, the electron beam is rastered across the analytical surface. The beam is screened across the sample surface. Actually, the raster is a rectangular pattern of parallel scanned lines from which we can get the images of the samples. So sometimes we can couple SEM and TEM instruments with other accessories like EDX called X-ray, energy dispersive X-ray accessory, so that we can analyze the presence of various elements present in the sample and corresponding percentage composition of the different elements. So we will be discussing in this lecture only SEM, that is electron probe method, to analyze the nanomaterials, to characterize the nanomaterials. So before going into the SEM in detail, let me talk about electron interaction with the matter. So when the electron beam hits the sample surface, there are many processes occurring. We used to call that processes as secondary processes, and the electrons ejected from the sample surface are called secondary electrons. So we call the electron beam as the primary source, primary electron, and what are the electrons ejected from the sample surface, they are called secondary electrons. So other effects are also there. So when we hit the sample surface with the high energy electron beam, there are several secondary processes occurring. For example, secondary electrons, backscattered electrons, Auger electrons, characteristic X-rays, transmitted electrons. So here I am very much interested in studying the secondary electrons and backscattered electrons, because so when we use the thick sample, so one can expect the ejection of secondary electrons and backscattered electrons, so which are useful in the scanning electron microscope. So in other words, the SEM instrument will detect secondary and backscattered electrons, and that electrons will be converted into images, corresponding images. Okay. So when we hit the sample surface with high energy electron beam, so sometimes one single scattering will occur or multiple scattering may be possible. Sometimes we cannot expect or we cannot get any scattering. So if scattering occurs, that scattering mainly depends on scattering cross section. Scattering cross section is depending on the material surface, the topography of the material, and the scattering is also depending on mean free path of the electron. So once the interaction happens, so we will get the pear shaped volume. That volume is called the interaction volume. So the volume, the depth is about 1 to 5 micrometer. So this volume increases when the beam voltage energy or the energy of the electron increases, and the volume of the interaction volume decreases when the specimen, when we use the high dense specimen or thickness of the sample increases. Okay. So usually the thick samples are analyzed or characterized using scanning electron microscopy, so which will detect both secondary electron and backscattered electron, and if we couple with the EDX accessory, we can detect characteristic X-ray, so which will show you the peaks corresponding to the different elements present in the sample. So when we use the thin sample, one can expect the transmitted electrons. These electrons will be detected using the instrument transmission electron microscopy. So along with the transmitted electron, there are other processes or other electrons also emitted: inelastically scattered electrons, elastically scattered electron, and diffracted elastic electrons, and X-rays, characteristic X-rays. So these X-rays will be used for the indexing crystal plates using the selected area electron diffraction. So these are the other secondary processes. Okay. So once the electron beam hit the sample, there are several processes. So based on the electron beam energy and the thickness of the sample, we can expect the different kind of electrons: secondary electron or backscattered electron, or transmitted electron, or elastically, inelastically scattered electrons. So thin samples are usually analyzed by the transmission electron microscopy, and we can analyze the sample with atomic level resolution using transmission electron microscopy. So that is depending mainly on the beam energy and the lenses and the detectors used in the instrument. So here the important secondary effect in the thin samples are transmitted electrons. So using that transmitted electron, we will be getting the images of the sample, the morphology and the topographical structure of the sample. And the elastically scattered electrons, they will be used for the simultaneous structural analysis by electron diffraction. So by means of this electron diffraction, we can get the crystal plates that H scale values we can find out from that image, from that result. And the characteristic X-rays emitted from the thin samples will be used for the analyzing the presence of different elements. So let me explain the important secondary effects which will be detected in this scanning electron microscopy. Okay, we will see the transmission electron microscopy in some other lectures. Okay, today I will focus on what are the secondary effects caused during the SEM analysis, and what are the different components present in the transmission electron microscopy, scanning electron microscopy, and how to prepare the samples and how it works, and what are the specific requirements for the SEM analysis, and some example images we can see in this lecture. Now, what is secondary electron? Secondary electron is emitted from the K shell of the atom. So when we hit the sample surface with the primary electron, so the inner shell, the K shell electron will be ejected. So that K shell that inner shell electron will be called a secondary electron. So after hitting the primary electron, that electron beam loses its energy. The energy of this electron will be decreased. Okay, after producing the secondary K electron. So the yield of the secondary K electron so will be more for even for the one primary electron. Okay, so when you for the one primary electron, there will be many number of secondary electrons will be produced. So from at which depth it is ejected, that is 5 to 50 nanometer depth of the sample. So from which the secondary electron will be emitted, and the energy of the electrons, secondary electrons may be 5 to 50 electron volt. Actually, primary electron beam will have the energy of approximately 50 kilo electron volt. So the secondary electron energy will be 5 to 50 electron volt only. So using the secondary electron, we can get the information about the surface morphology of the sample and topography of the sample, and particle shape analysis, size and shape analysis we can do. So these are the key information we can get it from the secondary electrons. And the resolution of the SEM image will be depending on the diameter of incident beam, excitation volume, and the incident angle of the beam. So these are the key factors. By optimizing these parameters, we can get the clear image, SEM image of the sample. And backscattered electron, one more secondary effects which will be used in the SEM analysis. So primary electron collide with the atoms normal to their path and scattered backward with a larger deflection as high as 180 degrees Celsius. So these electron will be called as backscattered electron. This scattering will be quasi-elastic, and the yield of backscattered electron usually less when compared to the secondary electron. So this yield may be depending on the local chemistry of the sample. So generation of backscattered electron relies on the specimen atomic number, interaction volume, and acceleration voltage. These are the parameters which will govern the generation of backscattered electron. So here the sample depth may be 10 to 100 nanometer, from which the electrons will be scattered back. And if only the elastically scattered electrons are selected, the resolution will be on par with the secondary electrons. So during this process, during the interaction, the electron interaction with the matter, if we detect elastically scattered electron from the sample, so that image will be the as pure as the image which is produced by the secondary electron, as clear as the image produced by the secondary electrons. So these secondary electrons will be the backscattered electron will be used for the topographical imaging, so which will be used to differentiate the areas of the sample. So usually the elements with the higher atomic number will look brighter, and it will be the backscattered electron also used for the analysis of mechanically allied materials. And this is another secondary effect which is producing when the electron beam hits the sample, but this is not directly related to the SEM analysis, but we can understand a little bit about the surface plasmon resonance. So usually low energy electrons are responsible for generating surface plasmons. This will be occurring mainly in the metal atoms. They have the valence electrons. So metals are highly electropositive. They will ready to give the positive charges. They can be easily that electrons will be easily disturbed by the interaction of electromagnetic radiation. So surface plasmon resonance is actually a dipolar resonance, or the coherent oscillation of the valence electron present in the metal with the incoming light, with the electromagnetic radiation. So it is the oscillation. So that is a coherent oscillation with the incoming light. So dipolar resonance is established as the free electrons on the metal surface oscillate in response to the electromagnetic stimulation. So this phenomena is well understood when we study the silver or gold nanoparticles. So they will show the typical surface plasmon resonance absorption bands in the visible region when we record the UV visible absorption spectra for silver and gold nanoparticles. So that peaks is due to these surface plasmon resonance absorption characteristics. And this is another kind of secondary effects that is called Auger electron. So Auger electron, so we cannot study the secondary effects step by step. So these all the effects will be happening all together. Okay, so when we get the sample, the K shell electron will be ejected. So that is called the secondary electron. So after creating the vacancy, the immediately higher energy electron will be trying to fill up this vacancy. So when this process is happening, some amount of energy will be released. That small amount of energy is required is enough to eject the electron from the outermost shell. So that electron, that ejected electron will be called as the Auger electron. So the Auger electron will have the energy of 100 to 1000 electron volt, and some authors, some books may be giving 2 to 50 kilo electron volt. So Auger electron emitted from near the top of the surface, with the sample depth approximately 0.3 to 5 nanometer. So these electrons are beneficial in analyzing surface chemical analysis, bond state and percentage composition of the elements present in the materials. The characteristic X-rays, this is another important secondary effect, secondary rays which are produced. So when the electron beam hit the sample, so one side there will be ejection of backscattered electron, the secondary electron, Auger electron, and during that process we can expect the emission of characteristic X-rays. So once the vacancy is created in the K shell, the higher energy electron will be filled up in that vacancy. So during that process, some amount of energy will be released as X-ray. So these are called the characteristic X-rays. The properties of this X-ray will be depending on the material which we are interested to study. So these X-rays are emitted from the sample depth from 1 to 3 micrometer. So this is semi-quantitative detection. So this X-ray intensity can be converted into percentage composition. So actually the X-rays may be emitted from K or L or M shell. So these X-ray excites the electron in the detector into the conduction band. So the greater the energy of the X-ray, the higher number of electrons will be ejected in the detector system. So that will be converted into the percentage composition. So that's why we can say the elemental analysis of micron diameter particles and large particles is routinely accomplished using these characteristic X-rays. So in all slides, I have put the title as electron matter interaction caused by the primary probe, that is the electron beam, and we are considering only thick samples since we are discussing the scanning electron microscopy. So I focus only on the thick samples. So thick sample means it will so majority of the secondary effects will be secondary electron, backscattered electron, Auger electron, characteristics X-ray. So we only talk about the electron probe method, particularly the scanning electron microscopy. In that microscopy we use only thick samples. So far we have discussed what are the secondary effects are possible when the electron beam hit the thick samples. Now this is the typical diagram for the scanning electron microscopy. So it will contain the electron gun, which is the electron beam producer, and we have the anode aperture accelerating voltage approximately 50 kilo electron volt. That kind of energy will be passed through the towards the electron gun. So that will contain some filament that will be heated by the that will be heated through this accelerating voltage. So electron will be produced. So there are condenser and objective lenses. The condenser lenses they will collimate the divergent beam of the electron beam, and objective lens is used for the detection process. And some special detectors are there: backscattered electron detector, secondary electron detector, specimen current, and so the detector will convert the sample surface, the backscattered electron or secondary electron into the image, and we will get the image of the sample surface. So if we have the EDX accessory, then we will end up with the different element, the presence of different elements and the percentage composition. So in overall, a high power electron beam originating from an electron gun near the top of the column is accelerated down a column through the sets of collimators and magnetic focusing lenses, and the detectors are placed near the sample surface. Many kind of secondary signals are collected and processed. So if an SEM has EDX capability, we can do the in situ measurement of elemental analysis, and we will get this percentage composition also. So we will just memorize this the picture, so that we can explain each and every components of the SE. So overall, this is the overall process. Electron produces the electron beam. The beam is focused to a diameter of 50 Armstrong by a series of magnetic lenses. It is scanned in a square TV type raster across the sample surface. The raster meaning screening the electron beam across the sample surface. So it will give some rectangular pattern like the results, the images. So secondary effects emitted are, as we discussed earlier, secondary electrons, backscattered electrons, and X-rays. These are the three important secondary effects in the scanning electron microscope. So after getting the secondary effects are these secondary electron, backscattered electron, and X-rays, so it will be detected and the signals will be amplified and displayed in the screen as the images. So this is the components of SEM. First one is electron gun. The filaments of tungsten or the lanthanum hexaboride, usually conventionally used as the electron gun. The filaments of tungsten or lanthanum hexaboride. So this heating of cathode filament by a filament current. The tungsten cathode is a wire filament, so it will have the V-shaped tip with the radius of 100 micrometer. So the heated filament will be producing the electron beam. The cathode is heated directly by the filament current IF. The electron exits the filament with the average energy of E approximately equal to kT. So electron gun materials are tungsten or lanthanum hexaboride. So it will be heated through using filament current. So that will produce the electron beam. So it will be focused using the condenser lenses. That will be, we will discuss in the another slide. So nature of the material. What is the prerequisite for the material to be analyzed using scanning electron microscopy? The energy necessary to facilitate the ejection of electron from the material surface is governed purely by the work function of that material. The material having less work function will be useful for the fissile ejection of the electron. So in that aspect, we can use the metal as the best materials for the electron emission due to the presence of free electrons in their surface. So field emission electron guns add extra energy by the application of electric field to the filament. So the field emission electron guns, this is more advantageous because it will give more current, more heat to the filament through the application of the electric field. So that's why some instruments it is mentioned as FE sum, field emission sum. So in that microscopy there will be a special guns, they are called field emission electron guns. So they will add more energy to the filament. Cathodic current density and brightness of the beam, how it is adjusted. So it is based on the Richardson law. That law gives the current density equal to directly proportional to the constant which is specific for the material. So AC is the constant, that is the characteristic of the material. 2 points we have to mention here. One, the electron, the current density to the filament, that is depending on the material constant and the work function. So when we have more material constant, so there will be a higher current density, and when we have low work function or less work function, so that will also favor the production of high current density, so that the filament will be heated fast and the electron beam will be created. So in that aspect, the most important cathode material is developed so far is the lanthanum hexaboride, for which the constant will be 40 ampere centimeter power minus 2 and K power 2, and the work function will be 2.4 electron volt. So in addition to that, we have Wienelt cap surrounds the filament and applies the negative potential that repels the electron, so that it will channel the electron beam through an aperture where the space charge is formed. So the Wienelt cap will repel the electron beam, so that the electron beam gets channelized towards the particular path. So the electrons are emitted as the point source called space charge, that is centered along the horizontal optical axis of the microscope, and the positively charged anodic plate serves to accelerate the electron through the aperture. So once the electron beam is formed, that will be channeled towards the particular path, and the positively charged anodic plate are serving to accelerate the electrons through the aperture. So these are the factors will affect the images, the morphology or the clear picture of the sample. So this will affect the brightness of the beam, that in turn will reflect in the image, the perfect image. Okay. In order to perfect the image, we have to optimize this the current density as well. So what is the purpose of having the condenser and objective lenses? The electron microscope are not made up of solid material. Actually, the optical microscopes are made up of solid material, but the electron microscopes are not made up of a solid material, but rather controlled by a magnetic field. So electron beam exciting the electron beam exiting the anode plate of the electron gun assembly is divergent. The electron beam exiting from the gun will be divergent. So that beam will be collimated using these condenser lenses, so that it will be focusing down the column and regulating the amount of the current. So many suns have two sets of condenser lenses, and in addition to the condenser lenses, we have objective lens which is located near the sample, that is also called as performing lens. So any imperfection or any contaminants in the column will be corrected by the performing lens or the objective lenses. So they are called as sigmators. They are special lenses that are able to compensate for the distortions caused in the column or any imperfections in the image. So that will be corrected through the special lenses, stigmators, and which is fitted or which is kept in the objective lens itself. So condenser lens will be collimating the electron beam which is produced from the electron gun, and there are other lenses, objective lenses. They are also called performing lens. So in which we have stigmators. So they will correct any distortions happening during the measurement. And the detector system usually some instruments having scintillator photomultiplier Everhart Thornley detector. So the secondary electrons are first collimated by a grid with an applied bias and impacted upon the detector surface. A short lifetime phosphor that is very efficient in converting electron into ultraviolet photons. So once the secondary electrons detected by the Everhart Thornley detector, so it will be converted into the ultraviolet photons. So that will be displayed as the image in the screen. So the number of electrons that reach the detector is a function of surface topography. So topography plays a main role in sending the electrons to the detector from the sample surface. So high points and surface features that face the detector produce more secondary electrons and hence a greater signal. Backscattered electrons are also detected by a semiconductor array located at the bottom of the column. So this detector, Everhart Thornley detector, will detect the secondary electron, and the semiconductor array will detect the backscattered electron. These are the two important electrons which are responsible for the image production. And the specimen current, a current is produced when the backscattered electrons strike the semiconductor array. So tapping into the specimen current is another way to acquire image. So most SEM samples are conducting. All the SEM specimens are fixed to a metal stage with a conducting cement or tape. So in some of the SEM microscopic measurements, the non-conducting materials will be made conductive using the sputtering technique. Usually they do gold sputtering on the samples so that it will be converted into conducting sample. So a specimen current is generated by inelastic scattering and absorption of impinging electrons after the secondary effects. So after the production of these secondary effects, there will be a specimen current will be generated by the inelastic scattering. That current is the function of the atomic number of the elements in the specimen. So there are a lot of factors. So when the backscattered electrons strike the semiconductor array, there will be a production of specimen current. That specimen current, depending on the secondary effects, for example, secondary electron, backscattered electron, Auger electron. So that absorbed current is a function of that depends on the atomic number of the elements present in the sample. Then finally, the image generation. Image generation occurs by rastering the electron beam across the sample, as we study already. A reconstructed image is sent to the CRT screen, cathodic ray tube, and viewed. So that specimen current will be converted into the image. So that is called reconstructed image. So which will be viewed in the display. So during the rastering process, there will be a dwell time. So at which the beam will be passed for some time. So during that the small time, the minimum amount of time, there will be ejection of secondary electrons. So they will be detected and they will be converted into image. So during the dwell time, the numerous types of secondary electron effects are expressed. The lifetime of the secondary effects will be shorter than the dwell time. So during that short time, the secondary effects will be detected, recorded and dissipated. So magnification, brightness and contrast all affect the image quality. So brightness is a function of entire image that is controlled by the amplitude of the signal, and the contrast is the variation of signal from one rastered point to the other. So that constant is equal to the change in strength of the signal between 2 points and the inversely proportional to the average signal strength. And cathodic luminescence is another imaging technique. The cathodic luminescence is also a secondary effect, so which is used mostly in the investigating luminescence from the mineral specimens. And the camera fitted in the column system takes a photograph of the emitted light from the sample. So far I discussed what are the components present in the SEM microscope and what are the different roles of that the components. The important components are electron gun and lenses, condenser lens and objective lens, detectors and specimen current and the image production, the reconstructed image in the CRT screen. So these are the main major components present in the scanning electron microscope. So how we perform, how the technician will do the will acquire the image by doing the sample preparation and everything. The operation of SEM is quite straightforward, although training is required to protect the maintenance high maintenance instrument and its expensive components. So it is easy, but we need to have some training before doing this, perform this experiment or this analysis. So sample loading and mounting begin by fixing the specimen to a metallic stub with graphite cement or conducting tape. This is important one. Conducting tape is important because samples analyzed in the SEM should be conductive, or we will make the sample in conductive nature. The stub is then attached to the metallic stage and placed inside the sample chamber. The chamber will be evacuated using the pressure 10 to 6 star in order to begin the filament warm-up process. A special procedure must be followed to engage the filament and align the beam. So acceleration potential is step up slowly. Once the beam current is detected and adjusted, the sample is introduced into the column and the sample is ready for the analysis. So these are the steps we need to follow before getting the SEM images. So this is the photograph of GEOL JSM 7700F field emission sum. So we have the field emission, which will give more energy to the filament so that the filament will be heated fast. So resolution of this instrument is 0.6 nanometer up to 0.6 nanometer size resolution we can see through that photograph at 5 kilovolt and 1 nanometer at 1 kilovolt. Using the 5 kilovolt acceleration voltage, we can go up to 0.6 nanometer resolution. If we use 1 kilovolt, we can go up to 1 nanometer resolution. So magnification capability ranges from 25x to as high as 2 million x. So this is the magnification. When we go higher magnification, we can go for the clear image or the magnified image. The acceleration voltage will be approximately 0.5 kilovolt to 30 kilovolt. You can use 50 kilovolt acceleration voltage also. So new lens system are able to correct spherical and chromatic aberration, thereby improving the resolution of objects. So it is capable of performing high resolution backscattered electron imaging as well as scanning, tunneling electron microscopic imaging of thin samples. So these are the SEM images which I got it for my samples I analyzed from my samples. So this is the silica nanoparticles. This is the same image. So you can see here the acceleration voltage 20 kilovolt and the magnification 15,000x, and this scale bar is 1 micrometer, and they detected secondary electron here. Yes, secondary electron image. And here the particle size is approximately 250 nanometer, and here the acceleration voltage is 20 kilovolt and 1,30,000 x the magnification, and 0.1 micrometer scale bar, secondary electron detection. And this is also one of my materials involving reduced graphene oxide, cobalt oxide and platinum nanomaterials. The sheet like structures you can see clearly here, that is RGO sheets, reduced graphene oxide sheets. On that we have cobalt oxide nanocubes. Here this is a FE sum, field emission sum. So we can go up to 100 nanometer scale bar. So here is the magnification is given, and here you can get the clear image for with platinum nanoparticles. So platinum nanoparticles are deposited on the cobalt oxide nanocubes. So both are present on the reduced graphene oxide sheets. So this is all about the scanning electron microscopy, that is the electron probe method, and what are the secondary effects which are involving in the SEM analysis, and what are the components of this scanning electron microscopy, and how to perform this the analysis of SEM, and some example of the scanning electron microscopic images. So thank you. We will meet you again in another lecture.